Yeah, our next speaker is Roberto, who is the Ralph W. Daunt Professor of Chemistry at Princeton University and also a faculty member in the Princeton Institution for the Science and Technology of Materials. Professor Carr is a leading figure in the computational physics and theoretical chemistry, well known for his fundamental contributions to ab-initio molecular dynamic simulation methods and other tools that we are using on a daily basis. He has received many awards, including the Raman Prize in Computational Physics from the American Physical Society, the Dirac Medal from the International Center of Theoretical Physics, the Sidney Fernbach Award from IEEE, the American Chemical Society's Award in Theoretical Chemistry, and he's also a member of the National Academy of Science. Recently, Roberto Carr has pioneered the application of deep learning in molecular dynamic simulations with great success, which I believe he will tell us about today. So his talk title is Boosting Ab-initio Molecular Dynamics with Machine Learning. Let's welcome Professor Carr.
Thank you. So in this talk, I'm going to present essentially why machine learning is very useful when you do molecular dynamics. And since this is a rather general meeting, let me just recall in a few words what is molecular dynamics and what is ab-initio molecular dynamics. So molecular dynamics essentially is a very useful simulation tool in which one solved numerically the Newton equation for the atoms in a system, and from that one can compute a number of statistical properties for that system. The trajectories in molecular dynamics derive from the potential energy surface, from the atomic forces that are derived from the potential energy surface. In standard molecular dynamic application, the potential energy surface is represented empirically by force field, by empirical force field that are adjusted to reproduce experimental or theoretical, known theoretical properties. In ab-initio molecular dynamics, the potential energy surface is derived on the fly from the instantaneous ground state of the electrons. So it is derived from first principle, and typically one uses Kohn-Sham density functional theory to describe the potential energy surface. The advantage of ab-initio molecular dynamics is that automatically can describe within the accuracy given by density functional theory chemical bond changes, and is therefore significantly more accurate than standard force field molecular dynamics. However, it is also significantly more costly. And because of that, its applications are limited. Now, to reduce the gap in efficiency between ab-initio molecular dynamics and force field-based molecular dynamics, machine learning methods have been introduced in the last decade, and many groups are now using machine learning method to model the interatomic potential energy surface originating from density functional theory data. In this talk, I will focus in particular on one such method that has been called the deep potential method, because it uses deep neural networks. In practice, as I said, these are somewhat shallow neural network, only few layers, are used to model the potential energy surface and other ground state properties that are accessible to ab-initio molecular dynamics. The deep potential method was developed in collaboration with Wenan. Wenan, in fact, introduced me to the power of neural network and machine learning. And in the application that I will discuss, several people contributed, but the driving force has been Linfeng Zhang, who was a great student in the PACM at Princeton, that I had the privilege of co-advise together with Wenan. He received his PhD degree in May, and now is in China. So let me just describe what we do. Essentially, in the deep potential method, we represent a function that, like an observable properties, that is a function of the coordinate of the atoms in the system. We give to this function a local, we decompose this function as a sum of properties that depend only on the coordinate of the atoms in a given local neighborhood. And whenever this is possible, this local property or sub I that is associated to a local neighborhood can be represented by a deep neural network. And in order to achieve that, F, that can be either, here I'm considering as example a potential energy, polarization, and polarizability. Potential energy is a scalar quantity. The polarization in insulator, the potential energy, we represent the potential energy in this way for any kind of material system. For the polarization and the polarizability, we only consider insulating material. So the polarization is a vector quantity, and the polarizability is a tensor quantity. So F is a function that is either a scalar, vector, or tensor, and which satisfies translational, rotational, and permutational symmetry, and is also a continuous function. We want it to be a continuous function of the atomic coordinates in an environment with variable numbers of atoms. The deep potential method achieves this goal by using two deep neural network to represent the local property, an embedding DNN and a fitting DNN that are optimized simultaneously. Let me just review very quickly. The scheme is actually quite simple in retrospect. First, what one does an end-to-end mapping from the coordinates of the atoms in the neighborhood associated to the atom I. So how is the neighborhood defined? Essentially, the neighborhood is a spherical domain centered at a given atom I, which is defined by a cutoff function. And what we do, we map the coordinate of the atoms in the neighborhood to a feature matrix D, which is an environmental descriptor invariant for translation, rotation, and permutation of the atoms of the same species, and which depend continuously on the coordinate of the atoms in the neighborhood. So we do that first by moving from the laboratory frame to a local frame centered in at the atom I that defines the neighborhood, and then the coordinate in the local frame are represented, the Cartesian coordinates are represented by a 4-vector, because we introduce a fixed function S of R prime of K, which is a function of the distance of the atom from the center of the neighborhood, which behaves like 1 over R prime K up to when it gets close to the boundary of the neighborhood, where it goes continuous smoothly to 0. So the ensemble of the coordinate of all the atoms in a neighborhood can be represented by this matrix Q that has a number of rows equal to the number of atoms and the number of and 4 column given by the component of this quadrivector. Then we define an embedding network E, which can be viewed as a matrix with m rows and ni columns. Ni is the number of atoms in the neighborhood, and this embedding network contain information on the environment in terms of the distances of the different atoms in the environment with respect to the center of the neighborhood. In terms of this embedding network E, we define the feature matrix D. Simply what we do the matrix product of E by Q, and notice that this matrix product of E by Q satisfies immediately the property of permutational invariance, because all the atoms at different distances occur, the information of the atom at different distances occur via a sum, which is independent of the order in which the atoms are in this neighborhood. We also define a matrix S that is the same thing as the matrix T, but only uses a smaller number of rows of the matrix E. This is indicated by this lesser E, and again, we do the matrix product of this lesser E with Q, and then we define the feature matrix simply by taking the product of T and the transpose of S. So we see that immediately at this point, rotational invariance is satisfied, because this product is a product of scalar. This is a matrix of scalar products, and the translational invariance is automatically satisfied by the fact that in the local framework, we refer everything to the center of the neighborhood. Now, armed with D, we can define then the fitting neural network, which is just a neural network that has D in input. This fitting neural network has one output when the property we want to model is a scalar property, and has M output when the property we want to model is a vector or tensor property. In terms of that, we can immediately define the potential energy, the polarization, and the polarizability surfaces. The potential energy surface is represented as a sum of local energies, each one of which is a truly many-body function that depend on the coordinate of all the atoms in a neighborhood, and the local energy is just given by this fitting network in this case. Now, you may wonder why is that always possible to define the energy, to decompose the energy in terms of local energy? Well, intuitively, one expects that one should have something like that simply because the energy of the potential energy is an extensive properties in the thermodynamic limit. But when we consider our system, this is an assumption that we make, and the fact that it's good or bad is evaluated based on the result. Now, for the polarization surface, we have again, this is a polarization for a system, a condensed system. We can, and here I'm considering just a case, the case of water as an example, but we could define the polarization in a similar way for other insulating system. We can consider system like liquid water or ice. For instance, here there are oxygen atom, hydrogen atom, and there are then the center of the electronic charge. For the oxygen atom, this is the dipole associated to the oxygen atom. This is the dipole associated to the hydrogen atom. The fact that this, I have 6 here is because in all these calculations, we typically use a pseudo-potential formulation to describe the system, which means that we only take explicitly into account the valence electron in the system. The core electron are frozen with the nucleus, and so they give an effective nuclear charge of 6 for the oxygen. Now, for the electronic contribution, this electronic contribution is given in terms of center of the Wannier function, of the Wannier distribution associated to the electron. This is well-defined property because they can be obtained by unitary transformation in the occupied subspace of the system. And in a system like this water system I'm considering here, there are Wannier function, this here WLI, there are 4 Wannier functions associated that can be associated to each oxygen atom. In terms of these 4, each one of those contain 2 electrons because we are considering a spin saturated system. And these 4 Wannier function, we can define in terms of these 4 Wannier center, we can define a centroid, a Wannier centroid. So what we have here, we have a local decomposition in terms of Wannier centroid, each one of which depend only on the coordinates of the atom in the neighborhood. Now, in this case, for an insulator, it could, the fact that this decomposition holds can be proven rigorously in physics by, in fact, it was done by Walter Kohn, who established a theorem that he called the nearsightedness of electronic insulating electronic matter. Is related to the fact that the system is gapped. Now, we apply the technique that I mentioned before, and we can describe this coordinate that of the Wannier centroid in the local frame in terms of this neural network, and here we do a sum over the index M, and the fact that there is L+1 means that the 3 last column of T are considered. These 3 last columns are associated to the Cartesian component of the coordinate of a given atom, and therefore they transform as a vector. For the polarizability, this is nothing else as the derivative of M with respect to an applied electric field in the limit in which this electric field goes to 0 by keeping fixed the coordinate of the atom in the sample. So then it can be written again in terms of the Wannier center or Wannier centroid, and can be and one has this local decomposition, and again by applying the technique that I just discussed, in this case we form a product that now transform as a tensor. Now let me I want just to add one comment here, and the fact that one has this decomposition in the case of a system like water is something that remained valid until the system remains insulating, which means that it is valid even if there are no longer water molecules that describe the system. So for instance, at very high pressure, the water molecule dissociate and the system become an ionic system that is characterized by oxygen and hydrogen ion, but the Wannier centroid still remain associated with the oxygen ion, even if the oxygen ion for instance, diffuse at sufficient temperature condition in which this system is an ionic liquid. So let me then say one more thing. In order to construct this neural network, we need to have a technique that is very efficient to optimize the network parameter. Since the neural network depend on ab-initio density functional theory calculation, we want to minimize the number of these density functional theory calculation because these are very expensive. So what we use an iterative model for training in which we take advantage of the fact that different initialization of the neural network lead to different local minima, so that we can define an ensemble of deep neural network. And so we initially train an ensemble represented by a few of its members, and we start sampling the thermodynamic condition at which of interest. And in doing that, we must have a criterion based on the network only that tells us when we need to acquire new data to improve the model. The criterion is the following. So we use, we label visited configuration when the deviation between the different members in the ensemble is maximal. So when the maximal deviation exceeds a certain threshold that is to be empirically set. By doing that, we keep exploring space using the computationally cheap deep neural network model, and only when we label configuration, we have to do then a new data acquisition, which again, by training, improve the model, and we keep going along this cycle until we achieve convergence. So this is basically the scheme that we have developed. And now I want to present very quickly a number of applications that are done at this Computational Chemical Science Center at Princeton that is supported by the Basic Energy Science division of the DOE. And this is one example in which we study the water titania interface, and we studied that both with ab-initio molecular dynamics and with deep potential molecular dynamics. You can see that with ab-initio molecular dynamics, it was only possible to study a small, relatively small supercell that include the solid titania interfaced or sandwiched with liquid water. And a significantly bigger system could be considered in the case of DPMD, and also a much longer simulation time. Only 40 picosecond simulation was possible with ab-initio molecular dynamics. 2.5 nanosecond and even longer is possible with deep potential molecular dynamics. The important thing that came out is that the water molecule in this system dissociate at the interface and give rise to a surface that is hydroxylated, so that has OH group attached that result from the dissociation of the water molecule. And this process of dissociation and recombination equilibrates until we have approximately 66% hydroxylation on average at all time. And here you see this is 20 nanosecond. The processes that give rise to dissociation of the water molecule have different time scale if we consider light water or heavy water, but the time scale is of the order of several hundreds of picosecond, which is definitely well beyond the time span of ab initio molecular dynamics. And so in this case, one could not detect any of these processes that are quite interesting. So this was just one example. Let me say another example that again shows the power of a deep neural network model. And in this case, we use a deep neural network model that describes liquid water. And we use this model to describe that is based on ab initio DFT data to describe metastable liquid water in the supercooled regime. Deeply supercooled liquid water is very interesting because it is it has been postulated that a critical point exists in this deeply undercooled regime. And if this deeply undercooled regime is there, this critical point is there, that would explain many anomalies of liquid water. So far, it has not been possible to reach this regime directly from experiment because the system crystallizes in the experimental timescale before one can make a measurement on the system at this deeply undercooled liquid in this deeply undercooled condition. However, it has been established that this liquid-liquid critical point exists with some empirical potential. And what we show here is that with a potential that has been derived entirely ab initio from quantum mechanical data, one obtains a system that is consistent with the presence of the critical point. In order to do that, we perform multi-thermal, multi-baric simulation, which are simulation in which one uses an so-called enhanced sampling technique in order to sample the system with a unique molecular dynamic trajectory. You see, we have here many data points at different pressure. These are isobars and at different temperature, but all these data points can be obtained with a unique simulation that is called a multi-thermal, multi-baric, because in this unique simulation, what one does is that one define the sampling in such a way that the sampling is uniform in this thermodynamic region. And then, since one knows the bias that one has to introduce to achieve this uniform sampling in this region, one can then unbias and get the real result. So what one can see is that all these data points that are obtained from this simulation can be fitted extremely well by a two-state equation of state model, and this two-state equation of state model predict a coexistence line between the low density and high density liquid, that is this black line, and that terminates at this critical point that is indicated by the red dot. Now, what I want to say is that these simulations are possible with machine learning, potential because we can definitely simulate several tens or even hundreds of nanoseconds, which is necessary in order to achieve sufficient statistics in this simulation. They will not be possible at all with direct ab-initio molecular dynamics simulation. Let me go to two more examples quickly. This is, I mentioned before that we can consider water. In this case, we consider ice under extremely high pressure. On the order of, we go up to pressure of the order of 100 gigapascal or more. When we go to this, you see this is at sufficiently low pressure. Here in this figure, one has what is called I7. This I7 is characterized by the presence of water molecules, so OH2, and as we apply pressure, this hydrogen dissociate from this molecule here in the center, and they go in the mid bond that connect the oxygen in the center. This is a BCC structure to one vertex here. And so at this point, one has what is called an ionic system. And very nice experiments were done in this system by measuring the absorption in the regime in which one has ICE10. This black dot in this figure are experimental data. This was a beautiful experiment that was done with diamond anvil cell. And what one sees in the region above 100 GPa, that is the one that we are considering here in this figure in the middle, one can see the black dot are the experimental data for the, there are essentially two modes that characterize the infrared absorption. One that is called stretching mode and one that is called deformation mode. And these two modes switch with each other as the pressure increases. This phenomenon is called the Fermi resonance, and this switching is due to the fact that is due to the strong anharmonic interaction between these two modes, and one of these two modes couples strongly with the volume, so that it increases its frequency by increasing pressure, while the other is relatively independent of the volume. And that is precisely what we see in this simulation here in the middle, and the red dot are the result of our simulation. They are not perfectly on top of experiment, but are very much in agreement with the general physical picture that is indicated by experiment. Again, this would not have been possible with direct ab-initio simulation. Final example, we can compute Raman spectra. This is another correlation function that has to be computed with the polarizability tensor. And again, one has a rather good agreement. At least all the important features that are observed in experiment are also present in the simulation. And what I want to say here is that this feature at low frequency compared to this feature at high frequency stretching modes have an intensity that is almost 2 orders of magnitude less than the intensity of the stretching mode. So you need a very good statistics to get this mode. And if you go to very low frequency, in which there are modes that correspond to the hydrogen bond network in the system, what the intensity of this feature is more than the 2 orders of magnitude less than the intensity of the stretching mode. Here we could study the dependence of this feature with temperature, and this mode at about 240 in the 200 between 200 inverse centimeter in the simulation and in experiment, approximately there. This mode is present, is associated to hydrogen bond network mode. This mode has an intensity that decreases with temperature as the hydrogen bond break as the temperature is increased. This is seen both in the simulation and in experiment. So these were a few results that I wanted to show. As a physical scientist, I'm most impressed by a method when it allows me to do something that was not possible with other methods, and which I can use to understand and predict experimental properties. There's been a lot of work in the development of this technique. All these techniques are available online in this DPMD kit and the software for the DPGen, the deep potential generator, and we are now working at constructing a deep potential library so that various people can add their potential to this library, and other people can use this potential for their system of interest. All that can be accessed from the website of the center. And let me just mention one other thing. Recently, again, Lin Fong, but particularly also Weili Jia, who is a postdoc at UC Berkeley, in the group of Lin, who was also a former student of PACM and is now a professor of applied math at Berkeley, have implemented, Jia and Zhang implemented, and other implemented the scheme on a multi-GPU system like on Summit, which was until recently the fastest computer in the world. And by harnessing the power of this computer, one can simulate a system of 100 million atoms by retaining quantum mechanical accuracy for, again, time scale that one can run 1 nanosecond, 2 nanoseconds per day for systems that are as big. That opened the way for applications that were simply inconceivable when doing quantum mechanical based molecular dynamic simulation. With that, I come to some conclusion. So, deep potential molecular dynamics is more efficient than DFT-based IMD by several orders of magnitude, and also scales linearly with size. The linear scaling with size is a consequence of the local decomposition. But DFT, the solution of the Kohn-Sham equation that is needed to get the ground state potential energy has an asymptotic cubic scaling with size. And so that is also provides a much better scheme for dealing with large system size. And this opened the way to studies that would be impossible with ab-initio molecular dynamics. At the same time, the scheme, in all the example that I showed, we could show that the accuracy of ab-initio molecular dynamics was not lost when going to the neural network representation. By harnessing the power of large supercomputer like Summit, one can reach such large-scale simulation. Now, are there issues? Well, of course, there are always in any good physical model, there are always open issues that one would like to address. One important issue has to do with the long-range effect. The atoms when we, in ab-initio molecular dynamics, one describes the system as a system of nuclei and electron. And nuclei and electron are charged particles that interact with Coulombic forces, and Coulombic interaction are long range. These long range interactions are eliminated in the neural network model, even though they are present. The neural network takes into account this interaction effectively because the ab-initio DFT data included those interactions by typically in terms of Ewald sums, but Ewald sums are not present in the neural network. So we were surprised to find out that in many systems like those that I described before, this long range electrostatic is not important, but does not seem to be so important, but there are examples in which they are important and they lead to specific properties that one would like to describe. So an issue of how to include long-range electrostatics in a deep neural network representation is an issue that is currently being tackled by many groups working in this area in the field of molecular simulation. Another effect that I did not mention has to do with dynamics of the atoms in the system. This dynamics of the atom in the system in molecular dynamics is treated by classical mechanics, Newton's equation, but in systems that include light atoms like water, there are known quantum correction that one has to include. This quantum correction can be included for static properties, essentially exactly using the Feynman-Kac path integral representation, and deep neural network are very useful in that context too. But in the case of the time-dependent correlation function that are needed to calculate dynamic properties like the infrared absorption spectra or the Raman scattering cross-section, one does not know how to include the quantum correction to dynamics in condensed system because one has an oscillatory term in the integral, and molecular dynamics Monte Carlo methods are not useful when one has to compute an integral of a quantity that is not positive definite. Finally, I showed before that there are deviation from theory and experiment, from simulation and experiment. These deviations are due in some cases by the fact that we were not including quantum correction, but mostly they are due to the fact that DFT is still an approximate method that relies on some approximation, on some approximate functional to describe exchange correlation effect. Can we improve the accuracy beyond DFT? I think that that is possible, and again, for instance, it's possible, and probably, at least in my view, the method that one should use to improve the accuracy beyond DFT is quantum Monte Carlo, which is, however, much more expensive than DFT, but using approaches like the DP-Gen approach to train a network, I think it should be possible to train a network with significantly better quantum mechanical accuracy as that provided by quantum Monte Carlo relative to density functional theory. That was the end of my presentation, and I want just to acknowledge the funding of the center provided by the DOE, and also the numerous collaborators who contributed to the work that I presented, who are all listed at the website of the center. Thank you very much.
Great, thanks, Roberto, for a nice talk. Due to time limitation, we have time for 1 or 2 quick questions. Let me read the questions.
So I can stop share.
Yeah, so how does your ab-initio potential for water compare with classical models such as TIP for P-ice in terms of computational cost per relaxation time?
Well, it is still more computationally expensive than TIP4P, but is more computationally expensive by 1-2 orders of magnitude. At the same time, is several orders of magnitude less computationally expensive than DFT. The advantage that, so some properties like these properties of the deeply undercooled water, their water dissociation is not important. And so there, one could use TIP4P, and in fact, people have used TIP4P. Pablo De Benedetti at Princeton is one of the leaders in studying these properties of water at deeply undercooled condition. And I've collaborated with him in the past using TIP4P or other SPC, other empirical force field. But I think that the fact that with a force field that has not been parameterized, one can get that, because not all force field has have the presence of this liquid-liquid critical point. And one thing that we would like to understand is what makes a force field having a critical point, a low temperature, a liquid-liquid critical point, and what not. And the fact that with the potential derived from quantum mechanics, one get that, I think is an interesting result.
Okay, great. There are a couple questions regarding robustness and so on, but I think we're running out of time. So maybe we'll revisit these questions offline. Thanks, Professor Carr, for a nice talk.
Thank you.